Good morning, everybody. Today we are going to be going through a quick review PowerPoint on the QCAA Chemistry Syllabus Unit 3 Topic 1, which is chemical equilibrium. So this covers everything from equilibrium into things like acids and bases and solutions and stuff like that. So the goal of this review session is to just have a look at all of the topics, just do a quick breakdown of everything, have a basic bit of information on each of the statements in the learning goals on the syllabus so that you can look at this and start to decide what you need to be putting your work into to be studying for this kind of stuff. So you're probably going to have a bunch of questions if you're not fully on top of all of these topics. That's okay. You can leave them down in the comments, anything like that. But the main idea is to just see where you're at in your understanding and be able to build off of that when you then go and do your own further study. Hopefully that makes sense. So we're just going to get straight into it. As I said, topic 1 is chemical equilibrium. So the first thing you need to know is what is an equilibrium. So an equilibrium is when the point of time in which the amount of reactants breaking down to form new products is equal to the amount of products breaking down to form new reactants. That doesn't necessarily mean that you have the same concentration of reactants and products. What it means is the forward reaction, the reactants turning into products, is happening at the same speed as the backward reaction, which is the products turning into reactants. So you'll notice if you look at the graph, let me just get my little laser pointer. If you look at the graph here, it's reached equilibrium when both of the lines flatten out and no longer go up or down. So that means that the forward reaction, products being created, is happening at the same rate as the backward reaction, reactants being created. And the position of equilibrium can be determined by the concentration of the reactants and the products. There are a number of factors that will affect equilibrium. These are the ones that have been specifically stated on the syllabus. So we have temperature, concentration, pressure, and catalysts. So you should have a really good understanding of the first three. Now, catalysts, individual catalysts for individual reactions are going to be different. So the idea is to just understand how it's going to affect the equilibrium, not necessarily understand what catalyst you need for every single reaction out there. So this is just a very quick breakdown of what all of those things do, or how they will affect the equilibrium. But on the next couple of slides, we're going to be talking specifics. So not going to talk anymore on this slide. Let's move on. Temperature. How does temperature affect the reaction? It depends entirely if it is endothermic or if it's exothermic. So if it's endothermic, it means that it needs heat in order for the reaction to happen. So reactants plus heat will form products. Because there's the heat on the reactant side, if you increase the temperature, you're adding more heat to the reactants. It doesn't want that. So it is going to favor the products. It's trying to get away from that heat. So it's going to move towards the products. So with an exothermic reaction, the temperature increase means it's going to move away from the heat and go towards the products. For an exothermic reaction, you get heat as a product. It's produced during the reaction. So what that means is if you increase the temperature, it's again going to try and get away from the heat, only this time it's going to be doing the backwards reaction. So it's going to be going from products to reactants. So it's going to favor the backwards reaction or move towards the left. So it's important for you to understand those two, endothermic and exothermic, what it means. How you remember that is up to you. If you just want to rote learn it, reactants plus heat equals products is endothermic, that's fine. If you remember, exothermic is things getting really hot, or the heat is exiting the reaction with the products. There's a lot of different ways you can remember it, but it's important to remember exothermic, the heat is on the side of the products, and endothermic, it is on the side of the reactants. And then the main key, no matter what type of reaction it is, the temperature is going to move away from the heat if it's increasing. If the temperature is decreasing, it's going to move towards the heat. Very important. Next, we have concentration. So very similar. All of these things, if you remember back to Le Chatelier's principle, which I haven't mentioned yet, but it's trying to move towards the area of least chaos, if that's understandable. So in concentration, if you're adding reactants or if you're adding products, you're going to be putting more things into a certain section of the reaction, it's going to try and move away from that. So if you add something to the reaction, it is going to try and move away from that. If you add heat, it moves away from heat. If you add reactants, it moves away from the reactants. If you add products, it moves away from the products. Same thing if something's removed. If something is removed, it is going to try and counteract that change by moving towards whatever was removed. So if you remove a reactant, the whole reaction is going to shift to the left and try and create more reactants. If you remove a product, it's going to shift to the right and try and favor the products and create more products. So whatever is being added or removed is going to have a big effect. So if it's added, it's going to move away. If it's removed, it's going to move towards. The big thing, the only big thing, if a reactant is added and that reactant is not the limiting reagent, it will not have an effect on the equilibrium. So if you are given a question on the exam that talks about adding a reactant, and in that question somewhere it's made you find the limiting reagent, make sure that you are looking at that. Because sometimes they do tricky questions, and I feel like that could definitely be one of the tricky ones they try and do, just to catch a few people out. All right, the next one's pressure. The reaction will move towards the side that has the least number of molecules when the pressure is increased. This is only for gases, doesn't matter for liquids or solids, but gases, the one that has the least number of molecules will be the side that it moves towards. So again, trying to move away from the crowded areas, if that makes sense. So the first example, 2A plus B goes to form 2AB. Equilibrium will move to the right as it has only 2 molecules while the left has 3. So we've got 2 copies of an A and a B, or 2 of A and B together. There's only 2 molecules on this side, so there's more room there. The molecules are trying to get to that side. If you have the opposite, so you flip it around and you have the opposite, 2AB forms 2A plus 2B, then you've suddenly got 4 on this side and 2 on this side, so it will move to the left to try and counterbalance. And yes, I do realize that they're not exactly balanced equations. They're just there to give a little bit of an example of what I mean. So I pictured this like if you and a group of friends are in one room. So you have 2 friends with you, so the 3 of you. And a lot of people come into that room and they're not your friends. Are you going to want to stay in that room? Probably not. So you're going to try and move away from that. So the pressure is like decreasing the amount of space you have in the room. So you're trying to move out of that place and get more room. It's hard to find an analogy for that one. That was a bit... Okay, so I didn't talk about catalysts here. So I'll just quickly go back to this side. So for the both forward and reverse reactions, the catalyst speeds it up. It doesn't change the position of equilibrium. It just makes it get to this point faster. So maybe instead of getting it to at this time, the equilibrium might be reached at this time, but it would be at the same concentration. So you'd get this same equilibrium constant. So a catalyst doesn't change the equilibrium. It just speeds up how fast you get there. All right, equilibrium constants, the formula. This is from the formula book. Kc or Keq, as some of you probably heard it, equals the concentration of C multiplied by the coefficient of C times by the concentration of D multiplied by the coefficient of D over the concentration of A multiplied by the coefficient of A times by the concentration of B multiplied by the coefficient of B. Words, that's hard. It's a hard one to try and explain in words, but it's not that hard. So you just write out your reaction like this, and the numbers in front of whatever your thing is, so this 2 will go up and become the little number at the top, and then that's it. The rest of it will be based on the concentrations. So you should be able to go from a balanced equation to this fairly easily. And I know last year's 2020 QCAA chemistry exam did have one that you just had to get to this stage and that's it. So the first step of these problems is get from this to this. The next step after that, so we've got a bit of a practice problem here. You then, with this one, you're given concentrations. You're given information. That means you have to try and find an answer. So if you were asked to just express the equilibrium reaction or equilibrium equation, you would just end up with something like this. If you were asked to calculate the problem, or you were given things like this, then you would need to actually answer the problem itself. So practice problem number 1, a mixture of H2 and I2, so hydrogen gas and iodine gas, is allowed to react at 448 degrees Celsius. When equilibrium is established, the concentrations of the participants are found to be 0.46 moles per litre for H2, 0.39 moles per litre for I2, and HI is 3.0 moles per litre. So at equilibrium, this is what it is. First thing you need to do is work out what your actual equilibrium expression is. So this is where you get your balanced equation, you find a balanced equation, you make a balanced equation, and you input the values. Next, you are then going to take your information that comes from the question that you're given. So in this case, we've got 3 moles here. We have 0.46 and 0.39 that are there. And you will notice that the HI has a 2 there because you have, if you have a balanced equation, you've got 2, so that means you need 2 of these. From there, you then put it further into your calculator. So you do 3 squared and then you multiply these 2 together and you get these numbers. And finally, you will get an answer, which in this case looks like it's 50. I think it's just cut off the edge there. So this is fairly easy as long as you get the correct equation and then you input the correct values. So if you can get all of that, you should get some points. And most likely this type of question would be a multiple mark question where you might get 1 mark for the correct expression, 1 mark for the correct inputting, and 1 mark for the answer, something like that. So it could be a 2 or 3 mark question. Sometimes you can't do that. Most of the time you'll be given a question where you know only some of the results. So instead of knowing both the products and the reactants, you might only know the reactants or something like that. So if that is the case, we then use something called an ICE table, or you may have heard it as a RICE table. In that case, we use the initial concentrations, the change in concentrations of the things we do know to work out what the equilibrium constants will be. So if you're given initial concentrations, this is most likely what you're going to need to do. So let's do a bit of an example for this one as well. So when 0.4 moles of PCl5 is heated in a 10 litre container, an equilibrium is established, which 0.5 moles of Cl2 is present. So the information that we've got right now, 0.25 moles of the Cl2 we have at equilibrium. So 0.2 moles of that at equilibrium. To start with, we had 0.4 moles in a 10 litre container. That might be important later, so I'm also going to highlight that. So that was our initial concentration. Looking at our actual... no, that's not my laser pointer. Where's my laser pointer? Looking at our actual start, we have PCl5 is what we have at the start. We have 0.40 moles of that. We have none of this at the start. We're starting with our initial reactant, this 0.4 moles. We don't have any of this yet. So what we are going to do is, first thing we need to do is put in our initial concentrations. So 0.4 moles of PCl5 and then 0 moles of the other 2. We know 2 things. Firstly, the final concentration of the Cl2 is 0.25. We know that. We also know that it is at a ratio of 1:1:1 in this equation. So whatever Cl2 is, the same can be said for PCl3. We know that. We also can use that to then work out the change, which is 0.025 moles. Because we know it's a 1:1:1, if these two have changed by 0.25 moles, we then also know that this is going to have changed by 0.25 moles as well. So for the change, it is going to be our 0.4 moles minus our 0.25. So if you calculate that, we've got 0.15, and then the other 2 are going to be 0.25 moles. Hopefully that made sense. Hopefully you've seen this all before, and this is just a brief overview. But the equilibrium concentration can be found through this. These are our concentrations for equilibrium. This is not the end. The end point is not right now. The first thing you have to do after you've done all of this is then get your moles per litre. So this is your moles, not moles per litre. So we know that it's in a 10 litre solution. So if we find our moles per litre, that is going to give us this information. From that, we can then input that into our equilibrium expression and find our answer. Hopefully that made some sense to you. Like I said, you should have seen this before. This should just be a review. If it's not, maybe I might do a bit of a couple of practice questions on that. But at the moment, we're just going to leave it off on that. That is the basic equilibrium information that you need. The next section is the acids and bases. There's a lot more in the acids and bases. It's a little bit harder. So let's go into that. So what are acids and bases? So acids are proton, which are hydrogen ion donors, and can be classified as monoprotic or polyprotic. Monoprotic if they donate one hydrogen, polyprotic if they donate more than one. The concentration refers to the number of moles in a volume, most likely moles per litre, within a solution. The strength is based on how much of the acid or base's ions are released in a solution, so how much it dissociates in that solution. So particularly in this case, the acid and base ions, we're talking about H+ or OH-. Bases are proton acceptors, so the hydrogen ion that is released by an acid will be accepted easily by a base. And strong acids and bases will dissociate completely in water, which means they'll break apart completely to become H+ and whatever else is a part of that acid, or they'll become OH- and whatever else is a part of the base. pH scale. This seems a weird title, but firstly we're talking about the Kw, which is the self-ionization of water. So water is one of those funky solutions that can act as both an acid or a base depending on what it is paired with. When it's paired with itself, it can in itself become an acid and a base. So essentially what that means is water has equal amounts of H+ and OH ions. So that information there, the concentration of that is going to be equal to 1 × 10⁻⁴, which is the water constant. So the self-ionization of water, that is the constant you'll get when you're multiplying the concentration of H+ by the concentration of OH-. Important later. The pH of the solution can be calculated using the concentration of hydrogen ions in the solution. So the pH is the negative log 10 of H+ ions. So if you can work out the H+ ions, you can work out the pH. The pOH is similar to pH, but tells you how basic a solution is. So instead of the pH with the concentration of H, you're looking for the pOH, so you're using the concentration of OH. This is where the information comes from before with the water part, 1 × 10⁻⁴. That number, 14, is kind of important because 14 is equal to the pH plus the pOH. So 1 × 10⁻⁴ is H+ concentrations and OH- concentrations. When we put that into a log of negative log 10, that essentially gives you the number 14 when you're adding them both together. I hope that made sense. So therefore, if you know the pH of something, you can work out the pOH. If you know the pOH of something, you can work out the pH of it, as long as you remember it's 14 minus whatever the other one is, or whatever you have. So this is how the pH of a base can be determined. Alright, so quick little checks. What is the pH of a 0.0235 molar hydrochloric acid solution? Remembering you're going to be using pH equals negative log 2H+. So just quick pause of the video, give it a go, make sure that you get it correct. If not, then you might need to ask yourself why you're not getting it correct or where you're getting it wrong. So hopefully, if I've done my math correctly, which sometimes I don't, but you should end up with a calculation that looks something like this. So pH equals the negative log of the concentration of H+ equals the negative log multiplied by 0.0235, which comes from the question, equals 1.629. And then that number there can be used for the next question, which is about the pOH. So if that is the pH of the solution, what is the pOH? We do the exact same initial steps, and then because the pOH is equal to 14 minus the pH, we can then work out that our pOH is going to be 14 minus 1.629, therefore it will be 12.371. Now, if you were looking into significant figures, you would recognize that that is not an accurate number of significant figures. So in this case, if we look at our significant figures, we are going to recognize that there are 3 significant figures in this case, the 2, the 3, and the 5. So we should really be cutting it off after the 0.3, so it would be 12.4 if you round it up. Same thing with this question here, it would be 3 significant figures, so it would be 1.63. That is kind of important in your external exam, so hopefully you've got a good grasp on significant figures. All right, next, what is the pH of a 6.5 times 10 to the negative 3 mole KOH solution? So again, it's giving you the molarity of the base this time. So this time we don't know the number of H's that there are, we know the number of OH's. So we're going to look at the pOH. So give yourself some time. Try and answer both of these questions, then we'll go through the answers. All right, so first thing we're going to do is we are going to find the negative log of the concentration of OH minus. In this case, because we know it is a strong base, this is the concentration of the OH minus. So we get it straight from the question, and it's going to give us the log of that number is 2.187. Again, if you were looking into significant figures, it would be 2.2. And then pH is equal to 14 minus pOH. So 14 minus 2.187 is equal to 11.813. So depending on how you're taught, you might do rounding a little bit different. I typically tend to keep at least 3 digits in there until I finish the equation and then round at the end. Other teachers will teach you differently. So depending on how you're taught, you should still get a close enough result. So that is our pH. A solution is created by measuring 3.6 times 10 to the negative 3 moles of NaOH and 5.95 times 10 to the negative 4 moles of HCl in a container, and then water is added until the final volume is 1 litre. What is the pH of this solution? This is a bit more tricky. You know 2 bits of information that are important in this one. We have both NaOH and we have HCl in this container, which means that you have to work out, after those 2 things have neutralized each other, how much is going to be left over of the one that has more. If you can work out how much is left over of whichever one has more, so whichever one is in excess, then you can work out the number or the concentration of the OH or H+, and then you can work out the pH. So that's the first step, is finding out how much do you have left over of the one that's in excess once you've used up all of the limiting reagent. So that's the first step. If you do that, you should end up with something like this. So obviously the HCl has a smaller number of moles, so that's going to be used up first, and it leaves us with 3.01 times 10 to the negative 3 moles. After that, don't know what I did that one for. Oh, because it is in 1 litre, we can convert it from moles of NaOH to molarity, so moles per litre. So that's what this one's for. On the left-hand side, it's moles. On the right-hand side, it's moles per litre. From there, that gives us the concentration of the OH minus, which gets put into our calculation, giving us 2.521. And that can give us a final pH of 11.479. And then in this situation, it is 3 significant figures, so it would be 11.5. So the Bronsted and Lowry model is specifically stated in the syllabus. Essentially, it's saying that the transfer of hydrogen ions can happen between conjugate acid and base pairs and conjugate base and acid pairs. So each acid will have a conjugate base, which is just the acid minus the H+, and each base will have a conjugate acid, which is the acid, the base plus a H plus, typically. So looking at these, you should be able to work out what the conjugate base of the acids would be. Again, it's just the acid minus the H plus. So I'll give you a quick moment. And the second one is what is the conjugate acid for the following base, which is, remember, the base plus the hydrogen ion that's released. Give you a moment to quickly go through it. Alright, so first one, if we remove the H, we end up with a ClO4, and remembering that H has a plus ion, so if you remove a plus ion, you're going to have a negative. The next one, NH4+, we're going to leave a H plus behind, and we're going to end up with NH3. And then lastly, we've got our lovely water. If we remove a H plus, we end up with an OH minus. For the opposite, with the conjugate acids, we're remembering we're adding a H plus on. So if we add a H plus to Cn minus, we're going to get rid of the minus and add a H, so we get HCN. If we add a H plus to SO4 2 minus, we're going to add one H and one plus, so we're going to get rid of one of the minuses and add a H. So HSO4 with one minus. And then for water, if we add a H plus, we're going to end up with H3O, and there is a mistake here. There should be a plus at the end of that. Hopefully that made sense. So that's conjugate acids and bases. Next we have buffer solutions. So buffer solutions are buffers are solutions that are conjugate in nature and resist a change in pH when a small amount of an acid or a base is added. So for instance, you might use, if you were taking HCN might be your buffer for something. That's very unlikely. So something that is a conjugate can be used to not have the reaction happen instantaneously. Le Chatelier's principle can be applied to predict how buffer solutions respond to the addition of hydrogen ions and hydroxide ions. So as excess H plus ions are added to the solution, the buffer will react to cause the reaction to progress to the left. Hopefully that made sense. It might make more sense if you look at it here. So the more concentrated the buffer solution, the greater its buffer capacity. So this is showing the pH of a solution when you add an AOH, so sodium hydroxide, to it. So if you have sodium hydroxide added and you just add it to plain water, you're going to start at 7 and instantly go up pretty much to 10 point something, and then it's going to go across until it reaches its equilibrium point. When you're adding a buffer, the idea is to give you more time to be able to add more volume so that you can more accurately pinpoint where the equilibrium point is going to, where the end point of the titration would be if you're trying to work out concentrations and stuff like that. So the more concentrated the buffer, the more of the sodium hydroxide you have to use before you get that nice curve up in a titration. Or if it's for something like you don't want the concentration to go up really high, you can use a higher concentration buffer and it's going to keep it down that point for a lot longer. Yeah, very, very important. Dissociation constants. So dissociation constants are how you quantifiably measure the strength of an acid. So strong acids and bases, we've already said, dissociate completely. Weak acids and bases don't. So these help you work out what point or how much of the acid is going to break apart and how much is going to remain as the original molecule. I hope that made sense. All right, so we got two problems here. We're going to be looking at how do we write the equilibrium expression first. So if we look over here, our equilibrium expression, if it is an acid, it is going to be the acid on the bottom and then H3O plus and A minus on the top. So whatever the two products are going to be at the top. If it's a base, it's going to be whatever the base is, and then the two products are going to be at the top. So you're always going to have two products at the top and one reactant at the bottom. So in this case, if we do that, we've got our acid at the bottom, HF, and then we got our two products at the top. One of them is the conjugate acid and one of them is conjugate base. Actually, conjugate acid, conjugate base. No, conjugate acid, conjugate base. I said it right the first time. So that's the first one. The second one, it is a base. So we're going to grab our acid, our base, which is the CO3 2-, which we know is the base because the conjugate acid has an added H+. And then both of these products will go on the end. So no H- and a HC3O-. So writing an expression, whichever acid or base you've got is written on the bottom. Both of the products are going to be written on the top. If you're then asked to find the pH of a solution, if it tells you the Ka, it means it is not a strong acid. You then need to use this process. If it doesn't tell you the Ka, it's a strong acid or base, and you can just go with that. All right, first thing you need to do, write down your reaction. Then determine is it a weak or a strong acid. In this case, it is a weak acid. From there, you can then write your equilibrium expression, which will be up in this corner here. So again, acid, both of the products. So acid, both of the products. Because it is a weak acid, we are going to be using another ice table to work out the concentrations at equilibrium. So when it's broken apart at equilibrium, what is the concentration of each of the products? So in this case, we don't know the end concentration of anything. We're trying to find that out. So what we do know is that we started with 0.01 moles of our acid. It's changed by minus X. We don't know by what, we just know it's minus X. And that means the equilibrium concentration is going to be 0.01 minus X. So we know that. The other side is where it gets a bit more tricky. We know at the end, the equilibrium constant, the products are both going to change by the same amount as the reactant changes. So the reactant is going to go down by a certain amount, and both of the products are going to go up by the same amount. That means that we can assume that the concentration of the products at the end is going to be X, which means that it has gone up by X and the reactants have gone down by X. I hope that made sense. So we can then put the information that we know from our ice table or rice table into the equilibrium constant. And yes, this is algebra, and yes, nobody likes doing algebra, but we can work with it. Because this number here is small, we can assume that X is going to be smaller than that. So X is going to be negligible. I can't say that word. X is going to be so small that if you minus it from 0.1 and round it, you're still going to end up with 0.1. So usually any number, if the concentration is below, say, 1, you're usually relatively okay to start cancelling, particularly if you've got a Ka value of such lowness. So we are going to just delete the minus X there, because we're going to assume that even with rounding, it's still going to be 0.01. After that, we're going to take the next step and start rearranging our equation. So we are going to multiply our Ka by 0.01, and we're going to get x2 from that. Once you do that, you can then find out what X is, and that information, X, if you look over here, this information, this is what plus H is, H plus is. So our concentration of this, our X, is the concentration of H plus in this solution. Therefore, the pH is that number, negative log of that number. So that's how you find the pH of a weak acid. Hopefully that made sense. This time we're using a 0.01 molar of HIO. Again, really small Ka values. So we're going to do the same steps. First step, balanced equation. Is it a strong or weak acid? Second step, write out your expression. Fairly easy. Third step, we're going to use the same table. So we've got the same information, 0.01 molar. That means it's going to end up changing by minus X to give us this, and then X for both of those. Hopefully that makes sense. Same thing, chuck it in there, and we're going to assume that X is negligible due to the small amount compared to 0.01. So we know that because of rounding, it's not going to make a huge difference. So I'm going to do the exact same thing we just did on the last one. multiply our Ka by 0.01. That's going to give us x squared, and then use the square root of that to determine what x is. Same thing as before, this x here is going to give you your pH. So your pH is going to end up being 6.3. So what does the Ka actually mean? The Ka value gives you a hint as to how strong the acid is. The larger the Ka value, the lower its pH is. This can be seen in the two examples we just calculated. So from those two examples, the first one was 10 to the negative 11, and then the other one was 10 to the negative 5. So you can very clearly see that the one with the smallest Ka value, so the less number of zeros between the decimal point and the first number, is got the highest pH of the two. This one's got almost a little bit more than twice as many zeros between the decimal point and it's got almost twice as much of the pH on the pH scale. It's not an exact science, but the bigger the Ka value, the more acidic it is going to be, because it's going to be a slightly stronger acid. Hopefully that makes sense. So if we look at indicators, an acid-base indicator is a weak acid or base where the conjugates have different colors. So for this one, H indicator means the indicator is a weak acid, and it is going to have one color when it's like this, and it's going to have one color when it is a conjugate. If the indicator is a weak base, it's the opposite. So BOH is the basic indicator, and then the color will be on the B plus will be the color, and the B over here will be not the color. Color A, color B. So one might be red and one might be yellow. Hopefully that makes sense. The pK of the indicator gives you an idea of the range in which the color will change, or the pKa. So in something like methyl orange, the pKa is about 3.7. They typically say a range of plus or minus 1 on either side. The book has a little bit of differences from that. So methyl orange, the range is minus 0.6 plus 0.7. So it's in the ballpark. So if you're given a pKa of an indicator, somewhere between plus or minus 1 is when that is going to change color. So you could just use that information to help you out. If you're told to let the answer to the question know what the range is for the color change, just look at your formula book. The only time you wouldn't do that is if you don't actually know, it's not in the formula book, and then you're given the pKa. Otherwise, just use the range that is in the book. Okay. So what indicator would you use? If you've got a strong acid and a strong base, that means that they're going to neutralize each other, which means the pH that the solution is going to change at is going to be around about 7. In which case, if a pH is around about 7, the indicator that you'd use would be around about that 7 mark. So you'd probably go with one of bromethyl blue or phenyl red, something like that. Because bromethyl blue is 6 to 7.6 and phenyl red is 6.8 to 7.4. Of those two, you'd probably go with the bromethyl blue because it's right in the middle of the range, whereas phenyl red, it's right at the start of the range. Weak acid to strong base titrations. So in this case, the weak acid is going to be a lot less helpful in neutralizing the strong base. So the pH is going to be higher. So it's going to be around about 9-ish. So for something like that, you'd go probably phenolphthalein. That'd be the only option in the formula book that you'd go for. So phenolphthalein, weak acid to strong base. If you're doing the other way around, strong acid to weak base, it's going to be slightly more acidic than neutral. So it'll be around about 5. So you'd go for something like bromoscal green or methyl red, one of those two. Depending on the exact pH you end up with, then you might pick a different one of those. Okay, volumetric analysis. This is your titrations. The endpoint is the point in which the titration is complete. This is usually when you want your color change to occur. The equivalence point is the point at which the amount of titrant is enough to completely neutralize the analyte. So the equivalence point is when the two of them neutralize. That is the midway point between the vertical bar in a titration. The end point is when the reaction ends and when you want the color change to be happening. Well, technically, the end point is when the color change happens, but it is the point at which the titration is complete. So you'll find usually after the end point, it tapers off very quickly. So looking at some curves, just in case you have to draw them. Titration of a strong acid, the equivalence point is going to be around about 7. So it's going to be pretty flattish until it gets to whenever that equivalent point will be. Then it'll go up and it'll be pretty flattish out of it. So it's a very flattish curve and then a straight center. Titration of a weak acid, it's a little bit more of like a hill that you're going up before you're straight vertical, and then it's flattish on the other side. So the strong base is going to show a flattishness, and the weak acid shows like a bit of a more hill that you have to climb up to get to first. The other side, this is a weak acid with a strong base. So this actually shows it more clearly the difference between the two. So this line here is the strong acid, and this is the weak base. So again, a little bit of a hill. Both of them are going to have a straight up and down, and for both of them, the equivalence point, the equivalence point for the weak acid is going to be here. The equivalence point for the strong acid, strong base will be in about the 7 mark. Strong base to strong acid again is the dotted line. The weak base, it's got a little bit more of like a hill that you have to go down, a little bit more of a gradient before it goes whoop, like that. Hopefully that makes sense. Hopefully you can clearly see that. You should be able to also draw that, knowing you should know where the equivalence points will be for a strong to strong, a weak to strong, or a strong to weak. You should be on top of that and understand those things, hopefully. All right, so, whoops, forgot to put thing on this one. Calculate the concentration of a 25 ml NaOH solution if 30 ml of the 1.25 molar hydrochloric acid is needed to titrate to the equivalence point. So, first thing you need to do, find the balanced equation. So you're told it's sodium hydroxide and hydrochloric acid. So if you write those things out, you'll find it's a 1:1:1:1. Very important. Next thing you can do is find the number of moles of the solution. So in this case, we know the concentration of the hydrochloric acid. We do not know the concentration of the sodium hydroxide. So we're focusing at the moment on the hydrochloric acid. So we have 30 ml of 1.25 molar hydrochloric acid. So concentration is 1.25. 30 ml we need to change into liters, so 0.03 liters. That will give us our number of moles. That information there needs to be used with our stoichiometry ratios. So it's a 1:1 equation. Therefore, it's 0.0375 is to 0.0375. So that is just a little bit of information. From there, we now know that the number of moles we have of sodium hydroxide is 0.0375. If we input it into our system, we can then use the same equation as we used before and just rearrange it. The concentration equals the number of moles divided by the volume. Therefore, 0.0375 divided by 0.025, and it gives us our 1.5 molar solution. Hopefully that all made sense to you. We'll do another example as well. So this one, equivalence point for 20 ml of a 0.2 molar solution, titrated with 0.1 molar NaOH. So how much NaOH will need to be used to reach the equivalent point? We're going to use the same steps. First one, balanced equation. Always start with a balanced equation. Then, if you're given numbers and you can, find the number of moles. That should always be your number one thing that you need to do if you're given numbers of some sort. Just sometimes it won't work, but if you're at a loss and you don't know what to do, find the number of moles. So concentration times volume, we know the concentration and volume of the ethanoic acid, therefore we'll use both of those. Same thing, volume in litres, so 0.2 multiplied by 0.02 is equal to 0.04. It is again 1:1:1:1 ratio, so 0.004 moles of that will make 0.04 moles of the NaOH, or needs 0.04 moles of the NaOH. From that, we can then find the concentration that we need of the NaOH. We know that we have 0.01 concentration solution. We're trying to find out how much volume do we need. So we're going to use the same equation, input the values, and then rearrange. So this number here, this number will swap over to there, and then this number will be swapped over to there. So we end up with 0.1 times 0.004, and we end up with 0.04 liters. So you would need 40 mils of the solution to equilibrium, to get it to equilibrium. Does that make sense? That doesn't look right, does it? So that would be multiplied by this, and then that multiplied by that, so that'd be, so no, it should be 0.04 divided by 0.1. Whoops. So that is the end. I hope you got something out of that video. If you did, please let me know in the comments. If you have any questions, please also let me know. Yeah, as I said, this is just a brief overview, not so brief with a 45-minute overview. It's just an overview of everything from the learning goals that you need to know for Unit 3, Topic 1. Hopefully that helped, and maybe gave you a bit of an idea of what you need to study in that unit before moving on to your own individual study. So thank you very much, and I shall see you for the next video we do on Unit 3, Topic 2.